Our first speaker this afternoon will be Nathan Millar, and he provides specialist environmental design and sustainability consultancy at Elementa Consulting for projects around the globe. His experience in a variety of sustainability frameworks, including LEED, BREEAM, Estidama, GSAS and QSAS, One Planet Living, and Living Building Challenge. He's going to be joined by Ed Garrod, who's a sustainability strategist and environmental designer at Elementa Consulting, and has been involved in many award-winning green global projects. He holds degrees in architecture and environmental design from University of Cambridge and an MBA in Innovation and Entrepreneurship from Imperial College London. He is a lead accredited professional and Europe's first Fitwel Ambassador. So we've got a great couple of speakers, so I'll pass straight over now to, I think, Nathan, who's going to speak first. Over to you, Nathan.
Thanks, Tim. So as Tim said, Ed and I work for Elementa Consulting, which is a member of Integral Group, which is a global network of deep green engineers. We are founding signatories of the World Green Building Council Net Zero Carbon Building Commitment, which our commitment is shown on the screen, which is 5 steps. Today is covering our 5th step, which is to be advocates for that scheme. As part of our work at Elementa, working with our clients to identify net zero pathways for all developments that we work on as far as we can. And this presentation is just going to show you some of the work and our experience of how we've managed to achieve net zero. So over the past 10 years, we've delivered a number of net zero energy projects, from cultural buildings to offices and even laboratories. And indeed, just on these 2 of these shown on the Packard building and also DPR headquarters building, one of which is Packard is a new build and the DPR headquarters building is a retrofit, were awarded the International Building Performance Awards by CIBSE. So again, recognizing through our experience of delivering these buildings. Now, we know that every new building by 2020 needs to be net zero, but we also know that this only represents approximately 1% of building stock at any one time. So in order to achieve the targets that we need to, we've got 99% of all building stock to be net zero by the year 2050. And so this is a huge task and a huge commitment that we need to achieve as a practice and as an industry. But everywhere is different. A lot of our net zero experience is in sunny California, whereby there's a little bit more availability from renewable energy technologies, such as from PV. But as we know, climates from around the world vary. This means that there's going to be different design responses in different parts of the world. And the dots just shown on the screen are where we have offices. We recognize that everywhere is different, and we need to look at individual developments and their context in order to be able to provide the design response and the strategies that are needed. But at the same time, everywhere is the same. We're on one planet, we're on one Earth, and this is the image of the Earth from the Voyager before it left our solar system, a tiny speck. But we know that the planet Earth is sick. We have a fundamental problem that we need to fix. There is no planet B. We don't have another option. As an industry, we need to move forward to deliver buildings, new buildings, but also retrofit and refurbish existing building stock to net zero standards. Unfortunately, though, there's very little extra money for delivering green buildings and net zero buildings. And so we need to look at this in a different way. Fundamentally, most clients don't decide to build net zero or commit to build net zero because of the energy saving costs that are going to be achieved. There's a number of different parameters that we need to consider. such as health and well-being and some of those other supplementary impacts that we can achieve through good design and good energy efficiency responses. But we do have reasons to be optimistic. So we are well past the bleeding edge of technology. So if we take the development of a portable tablet, and this was first developed by Microsoft in the year 2000, which was a touchscreen tablet, but it wasn't until the year 2010 when the iPad was launched where this was actually brought to the market and rolled out across the globe. And this is now a piece of technology that's in pretty much every single household, whether it's an iPad or similar. So we've done the innovation, we know how to get there. We do need to accelerate, but the most important thing that we need to do is to find out what works, which in many cases we do, and we just need to replicate that as much as we possibly can, doing it over and over and over again until we achieve the targets that we need. So this is just a cross-section of a few of the developments that Integral Group has been involved in. So one of the first net zero projects we have was the Ideas headquarters building. Now this was achieved at market cost, but it was important to consider that the availability of large PV grants that aren't always in place. But as we've moved forward from that to DPR and Indigo Way, which are shown and highlighted in 2014 and 2015, these are both delivered at market cost. They're both retrofit offices. We'll come on to a little bit more information on one of these projects on some of the strategies that were used and implemented. So we know what the business as usual is, and we know that we can no longer build to that. As an industry, we know that through our knowledge and our understanding, we have for free the possibility to integrate passive design solutions, create behavioural change of building owners and occupiers. And we also know that if we carefully consider the systems that we put in buildings and maybe switching fuel typologies, we know that we can achieve additional benefit at low to zero cost. And then the final part of the puzzle, that operational carbon that we have left over, we need to obviously move towards 100% renewable energy. But we also know that the cost of that is falling year on year. And so through all of these different interventions and strategies, we know the pathway that we need to follow.
Hi everyone, Ed here. That graph makes it look incredibly easy. The reality is that it's only possible through an integrated design approach. And so as building services engineers, sustainable design consultants, we have an important part to play, but success is entirely dependent on a close collaboration with our clients, with a deep understanding of the end user, working with great contractors and architects who really understand the value of integrated design. And so we've developed a pathway that we try and follow on every one of our projects, whereby we seek to embed the net zero target from day one. And the value of that is in setting that stretch goal is it can transform projects whether or not they actually achieve net zero in operation. It changes the fundamental way that we approach design. So I'm going to take you through this process with some examples of how we work. It's important to remember it's iterative. So as we discover information and we discover how we optimize a building throughout the design process, there is opportunities to weave back in and take that learning to change the way that we design. So from the get-go, we need to make sure that net zero is embedded as a target from day one. This is incredibly important when we talk about setting the mission statement or agenda for a project, and it encourages us to start thinking about how we reach that target from the outset. And a key part of that process is to bring the entire design team together. So as many stakeholders as we can, people that will be affected by the building in use, those that are developing it, the contractor, across the board, to bring them together to understand how a net zero target sits within broader sustainability aspirations and how it can actually support the delivery of other important aspects of a project's brief. We do a lot of work to make sure that the analysis tools that we have at that early stage are incredibly low cost, incredibly quick and responsive. Here's an overheating analysis tool that we run for residential projects in the UK to look at criteria that we can apply before there's even a building design. We can start looking at glazing ratios, risk of overheating, and how that works with a net zero target. We also need to deeply understand how buildings will be used. If we rely on the occupancy patterns that we're given in profiles for energy modelling, so on this slide here, you'll see in the middle there's that classic camel hump shape of occupancy profile that you see assigned in this case to a typical office building, and above it is the real occupancy profile that can be divined, if you like, by going to look at what Google are doing. So if you look at Google Popular Times data for a building, you can see when people go in and out. That phone in your pocket is tracking where you're coming in and out, and you can use that to see how very much different occupancy patterns will be for a building. So in this case, you've office buildings that are actually have a significant amount of out of hours use, a long tail into the evening, and even use over the weekend that wouldn't be accounted for within a simulation approach. So real performance data informing simulation, and down below there you have our occupancy levels for our office in Oakland compared to code expectations that are placed on them for energy modelling. So we need to understand when buildings are actually being used rather than the hypothetical. Part of that is knowing then what people are doing within those buildings, and the assumptions that we use within simulations typically reflect plug loads that are very much out of date. So the trend has been a dramatic reduction in those loads, and that also then drives different approaches to system selection. So in the case on the right hand side there, the plug loads of the Packard Foundation, before they moved into that building, by going and actually measuring every single device, each photocopier, each PC, and seeing where the demand comes from, you can look at huge opportunities to reduce those demands. And that is an even bigger opportunity when we look at high intensive environments like labs. So when we really understand the building, we also need to understand what's happening outside it. So what opportunities are there for us to connect into other sources of energy, waste heat, opportunities to connect into bigger systems that could reduce our footprint. And so the next slide is just an example of some of our thinking for a project in Luxembourg that we've been looking at, where when we see the entire development as a whole, we can start taking waste heat from one use, from residential or hotel use, passing that to office use, looking at how that affects the operation of retail buildings, looking at car parks as thermal stores, how we can create low temperature ambient loops by which to share energy, and using heat pumps to avoid the need for combustion. So none of these systems would work in isolation unless they're seen as part of a bigger overall integrated solution. We also find that when we get into the stage of testing strategies, it's more and more important to do more with less with the analysis time that we get given. The design cycle that we typically see for projects is getting shorter and shorter and shorter. So the need to understand and predict performance quicker and quicker with a high level of accuracy is more and more important. This is just a case of doing some advanced CFD work, actually using fire dynamics simulation approaches rather than conventional CFD to understand how systems might work, how comfort could be achieved. And the agenda here really is about, wherever possible, back to that original bar graph, can we drive out costs from the systems themselves and pass that and those cost savings back into the architecture? The architecture being there for 50 to 100 years, the systems typically having a life cycle of no more than 15. It's really important that those embodied aspects of the building, the passive elements can be there. But to also think about the embodied impacts of those decisions too. So the skin that we choose has a carbon impact, and the carbon emissions associated with construction are being released now, whereas the operational emissions that we're designing for are over a 50, 100-year period. So thinking embodied is just as important in many respects as thinking about operational. We need to change the way we think about how buildings breathe. So rediscovering the power of fans. There's a big ass fan there over in the top left. Very, very low energy, high levels of comfort without resorting to conventional mechanical systems. We work with technologies like thermofuser, where we have automatic control of ventilation rates based on temperature without the need for additional smart systems. Thinking about which parts of a building don't actually need to be mechanically ventilated, and using smart systems where they're relevant to the end use. One of the things that we found is incredibly important is the need for MEP engineers to talk the language of the rest of the design team. And so we started doing a lot of work visualizing how our systems will look in a building, and so that we can compare options. Here's for a mass timber project we're looking at the moment. So the architectural objective as well as the structural objective is to see that slab, to see that structure. How could a low energy underfloor air distribution system interface with that? What would it do to the look and feel of the skin above? How would it change our experience of that space as well as working towards net zero goals? So the need to understand what your audience requires is part of our ability to change their conversation towards exploring options that might otherwise have been not up for consideration. So your building's in place, you've got the skin working really well. We've thought about how we connect to other systems, how it's being behaved. We've then got the opportunity to look at how we can generate energy on site. And this is from the Packard Foundation, the roof. Other presentations we've got the actual track data over a number of years showing a net positive generation over the course of the year. So that's net zero energy on site, generating more energy in a year than it actually consumes. Opportunities will differ. It's not always going to be the case that you can integrate renewable energy on the building itself, and we have to move away from being incredibly dogmatic about where our renewable energy comes from to accept that near site, off site, and within the grid district has a just as big a part to play as integrating renewables into buildings, because ultimately the planet doesn't care where those carbon emissions are saved from, just that they didn't happen in the first place. And the cost of renewable energy is plummeting. We're seeing the cost of panel prices continuing to fall. It's incredible, the pattern there, and this is what's being shown in that graph. We're also finding at the same time that the ability to purchase power at a utility scale is getting to the point now where it's certainly cost competitive with coal. We're finding that across many different grids, it's more economic to put renewable energy systems in place than it is to use conventional fossil fuels. So whilst the grid is decarbonising, that provides us with an opportunity to do buildings that are both lower energy consuming but also lower carbon footprint. Storage costs are also plummeting in the same way, and this is actually being driven by the rollout of electric vehicles. So the waste battery storage that we have after the end of life of electric vehicles is taking the cost down, and just the scale, every time we double the scale of battery production, costs fall by about 20%, and that's set to continue. So storage is becoming cheaper at a grid scale. In Australia, we're seeing it being used to manage peak flows. And we're seeing decarbonisation in general across the globe. Some economies taking a slower move to decarbonise their grids, but the demand for us to reduce the consumption of buildings has to be done in parallel with our cleaning of our grids. And when we have our buildings in place, it's incredibly important that we take a soft landings approach throughout the process of design, but also into operation, so that we can be commissioning our buildings and fine-tuning them, as they are complex machines, so that they operate better and better year on year as we discover more about their performance characteristics. And then in operation, we have to stop being scared of the data that can be collected. It's gone are the days when we should be worried about bad news coming from buildings. That data is being collected on performance all the time. If something's not working, it's our opportunity as consultants, as engineers, to get back in there and find out why. And also to understand that occupants have so much more data at their fingertips now that if we don't have a proactive response to operational performance, we will hear about it from occupants in any case. And with that performance data in hand, to then disclose it. And the power of transparency is really important here. If you make a public commitment to head towards zero, if you track that data and make it public, you're much more likely to keep down on that commitment. I'm going to quickly give you a little bit of an overview of 435 India Way. This is a traditional tilt-up construction, only single story, so lots of roof area for PV, so in some respects an easy task to get it renewable. We punched holes in the roof to get great daylight in there. These are actually south-facing roof lights. We've got fans being used, night purge ventilation, exposed thermal mass. It's insulated on the exterior of the building. The space that we create, the quality of the space has attracted tenants very quickly. And what we find here is this Kevin Bates, our client. We're now, I think, on our 4th building with him. this is when you start seeing the economic benefits, and this is purely on the basis of going for a net zero building. So yes, there is a premium compared to doing a business as usual approach of just putting conventional systems into that space. But when you take into account the operating savings from that building, the ability to market and rent that building quicker and at a higher value, you have an ability to generate positive flows of income into that developer. So from a development point of view, it starts to show a net benefit, without even taking into account some of the side benefits in terms of lower reserve capacities and utility connection costs. And Kevin is out there telling the industry that the payback period for this strategy for these buildings is only 3 to 4 months, and in this case a $2 million net benefit from taking a net zero energy approach rather than a business as usual case. But these figures really start to hit home when we talk about people, because the reality is that energy costs are absolutely dwarfed by the cost of people's salaries. This is in the London situation. Typically, you'll hear people say it's 100 times the cost of energy is the cost of the people in a building. If you use figures for London, it's about 158 times. And depending on the salary profile of the people that are within a building, it can be 200-300 times higher in particularly in knowledge-intensive spaces. This is just an example of a project that we've been looking at in the UK, where we had the chance to work with the Chief Financial Officer to look at those people metrics that come into a building and how they could be affected by good passive design and radical energy savings. So in this case, we could understand what's the turnover rate for this company, which is actually very high, pretty high levels of sickness in this space. If you could work to reduce those levels by using best practices in lighting, daylighting, ventilation and comfort, there is the chance, the possibility, with a big error range of a £3 to £4 million a year saving, and that dwarfs the £37,000 a year that we were able to achieve by a 70% reduction in energy consumption. So the net zero strategies have bigger impacts financially on the people than they do necessarily on the energy bill. And then going back to DPR construction, which is the CIBSE award-winning project, it's a conversion of an existing warehouse, very deep planned space, again getting light in from above, keeping the existing structure, so the embodied carbon savings of keeping that structure there. Big open plan workspaces, lots of biophilia, really popular space. It's being occupied to a much higher level than we could have predicted because it's loved so much by its occupants. And critically, it's operating in net zero energy, certified, verified by end of the year data. But when we ask people in the building how much satisfaction levels they are, so we can measure that using the CBE Indoor Environmental Quality Survey method, it's consistently around 20% higher performance across the whole range of criteria that we look at. So net zero energy and much higher levels of satisfaction.
So in addition to providing energy savings and also the impact that it can have on the occupants of the building, there's other tangential benefits that we've also seen with some of the developments that we've been working on. Now, this is a hospital building designed in Beirut. Now, we set a target that this would be net zero, and it won't achieve that target. But what it has led to is a rational facade design which carefully considers the comfort of the occupants within the hospital rooms. So this is for cancer patients and patients' recovery as well. So being exposed to solar access causing discomfort is an acute issue. Now, we've got supplementary benefits with regards to this facade design. Not only are we maintaining the comfort of occupants within the space, but we're also cutting the energy that within that space that is required through solar shading and a high performance facade. Now, by code in Beirut, for a hospital space, hospital rooms are sealed. It's a 100% mechanical ventilation system. And so we really work with the client to challenge this design. Is this what it actually needs to be, or can we deliver a building that can actually breathe, that can utilize natural ventilation when required? So this is a rendered example from another building that this is a Perkins and Will building who we're also working with in Beirut. And this is one of the design responses that they've got. And you can see just from this render how natural ventilation has been built into the design. And so we transferred this philosophy to Beirut. And what we actually found is not only can we deliver a building that is energy efficient, but given some of the energy security challenges that are also faced within Beirut currently, when there is a power outage, we've found that through the use of natural ventilation, we can then provide a building that can be opened up, that can survive, that has passive survivability, meaning that we don't have to decant patients from hospital beds. They can stay there. Obviously, the temperature profile will slightly move up, but within acceptable bounds. But what we also found and identified is from the backup power fuel reserves that are inherent within the design and the delivery of that building, meeting the client specification, as opposed to having backup power that would survive for approximately 3 weeks, we've actually got backup power that could survive for 3 months. And this offers the client a much better approach to the design of this building. And so these are some of those tangential impacts that we've been speaking about when designing for, that come inherent when thinking about designing for a net zero building. And obviously we've been speaking about international projects. So let's bring this to the UK context. And what we've also found is this allows another form of communication that we can have with regulatory authorities, particularly over planning commitments and planning targets that are set. So this is Hackbridge School in London, and you can see BEDZ just on the left-hand side of the screen. Now, as part of the design and the delivery process, we spoke with the local authority and with the client, and we were deciding whether, how could we provide an offset? Could we take the money that would be spent on the BREEAM certification, which through designers, good designers, a lot of those design requirements are inherent in what we do in every day. Could we take, for example, those consultancy fees, those additional fees for registration, those additional fees for providing the evidence and uploading all of that evidence? And could we say, we want to transfer that cost with the client to delivering a net zero building? And that created this really interesting conversation and quite a new narrative as well with the local authority, and they accepted that proposal. So what we are looking at here is obviously the render of Hackbridge. Some of the design strategies that are being used are energy piles for energy heat and cool. And you can actually see on the Bruckle in the top right, we're actually achieving a minus 25 Bruckles score. So delivering an A+ rated building. Now this is from photos taken from the last summer. And the building will actually be opened September this year. But what we've also got here is a conversation about how we can widen our views of carbon and zero carbon within buildings. So for example, here we've got timber construction, so we've got sequestered carbon within the structure, lowering the embodied carbon of the development from the get-go.
So when we talked about the need to embed net zero as a target at the beginning of a project, sometimes we're lucky enough to work with clients who are already working along that journey. One of those is San Francisco Airport, who've been a client of ours for a long while. They've set themselves a goal of being net zero carbon by 2030. And to achieve that means that their entire building stock needs to transform the way it works, so both existing buildings and new buildings. And one of the buildings we've been working with them on is a office administration building, I think it's landside, which is used as part of their administrative facilities. It's a building that from the outset had a net zero energy target, and embedding it that way means that you have some interesting conversations around how we integrate both architecture and systems and people's behavior to achieve that. And the result has been we've dramatically reduced the cooling requirements of the building. So the chillers are half the size than would be expected, third the number of VAV boxes that you would expect in a building of this type, and the AHUs are a quarter the size because we're using a DOAS system, so 100% fresh air, just dealing with the ventilation loads. with the heating and cooling requirements being addressed by radiant systems and fans. So you'll see there, we've got an exposed slab. We're thinking about the acoustics, how you deal with those spaces that would otherwise have issues with audibility, so that we can activate that thermal environment. So you've got, go to the next slide. This is a view from inside the building, looking at the edge to see the facade working pretty hard there. We've got carefully considered shading systems to make sure we were managing the solar gains. You'll see on the right hand side there, those sort of darker pockets in the ceiling. Those are fans, where the fans are directing air upwards rather than downwards towards the occupant, so that they wash air across the thermally activated slab, which has got a hydronic system embedded in it, so that you can increase the output level from that slab without getting downdraft risks. And so when you pull this all together, you've got a really carefully considered integration of the radiant systems, the cooling strategies. You've got a skin that's working really hard to reduce the load. You've got better quality air, but it's 100% fresh air. You're not having to recycle air. So the air quality, the environmental quality is higher, and you've got a building that's dynamically responding to its environment. Here going slightly crazy on a loop on the right hand side there, with the shades operating in response to solar exposure. So essentially you get to these projects where everything starts to work together, where the costs come down. They come down because you've got that close collaboration from the outset, a clear goal where net zero is embedded from day one, and the ability then to work as a design team to hit those targets and work with a contractor to deliver them. And I believe we finished very early, so we can have lots of time for questions. So Tim, hopefully there's been some questions put into the panel and we'll be able to address those now.
Great. Well, thank you very much for that. And yes, we have got some questions. So I will pitch straight into that, into those. There's still opportunity to ask questions. So if you haven't yet asked a question, or if you've asked one, you want to ask another one, please type into the question box, which is on your screen now, somewhere, probably over on the right hand side of your screen in the control panel. So feel free to type questions in, and I'll work through these questions. So there's a question that's been raised by a couple of people, and Dennis has asked this and Carl has asked this. I won't work down anymore, but they've asked, what is your definition of zero net energy buildings?
That's the very obvious question to ask. So the challenge is that there are many definitions out there. So the definition we've traditionally worked with in California has been net zero energy, based on the idea that you're generating as much energy to meet your on-site needs as you're consuming in a year by renewable energy delivered at the building itself. So that's much more aligned to the Living Building Challenge approach to defining net zero energy, and it also embraces the idea that you shouldn't be using combustion systems on site. Now there are many different versions of what net zero energy means within California, globally. In the UK we've always talked about net zero carbon, so looking at how we convert energy consumed within a building via carbon factors for each of the different fuel types, and then looking to offset and balance those through different measures, whether it's renewables or swapping out fuels. And so the answer is that by and large we have been using the net zero energy definition of energy balance over a year for the projects that we have in North America, and then globally we're moving much more quickly towards a net zero carbon definition, which is the one that's been developed and we helped to develop with the World Green Building Council. And that's to say that you need to have there's a hierarchy by which we have to achieve radical reductions in energy demand. We then have to increase the efficiency by which we supply energy to buildings. We have to generate energy renewably on site to the point of it not being economically viable or technically feasible, and then after that you mop up the rest through other metrics, and that can be by purchase of renewable energy credits, by investment in off-site renewable energy, and in some cases by offsets. And what the World Green Building Council has done is it says that in each region we should allow industry or government, depending on the case, to define what net zero carbon means for it. So as long as the end result is that we have no net zero climate change impact through operational energy consumption, then they're quite flexible about how different jurisdictions develop their response. And so we find that within each region we work within that framework.
Okay, thank you. There's quite a lot to think about there, and I think I picked up there at what you said about not having combustion on site, which one of the questions that's come in, zipping down towards some of the end of the questions that come in at the moment. What this is from David, and what's your view on biomass? And I presume it means on-site biomass.
Actually, I might ask Nathan to show some slides that we had hidden, actually, because we thought we'd run out of time, but we had some slides talking about unintended consequences. And one of the issues with biomass is that if you think about the planet as a whole, if everyone was to burn biomass as a way of providing the heating or generating electricity, what would the air outside look like? And the answer is not very good. So if it doesn't work for everyone, it probably shouldn't work for anyone. And the reality is that what we saw, particularly in the UK context, is that fuel switching towards biomass was massively encouraged. So in London, we saw a big shift away from conventional gas boilers towards the biomass combustion. A lot of the times that was pelleted biomass that had actually been shipped in from Canada. So we weren't thinking necessarily about the embodied impacts of transporting that to site. But not only that, even with the best of your air quality systems for scrubbing the exhaust and that, you do have local air quality impacts. And so London in 2015 started to look like this. And then equally, when we think about biofuels, when you dig deep into the downstream effects of generating biofuels by offsetting habitats or by offsetting food production, you end up finding that the carbon footprint of typical biofuels is about 3 times higher than if you were just burning gasoline. So we've had this habit historically of shifting the burden rather than actually addressing the problem. So if you rely on switching fuels to another form of combustion, you're just moving the problem somewhere else. Whereas if you move to an all-electric approach and think very carefully about the embodied impacts of the refrigerants you're using, it's a really big concern. You can start then to look at renewable energy, renewable electricity meeting electrical demands rather than allowing ourselves to continue with any form of combustion.
Okay, thanks for that. We've got loads of questions coming in, so I'm trying to give them some, keep a thread running. And this one again is from David. I think maybe the same question as last time. But what net zero terminology is used for CO2 factors, as it's always changing, and how do you account for that in the long term? And we're obviously seeing the carbon impact of electricity is dropping and probably tailing out now in the UK. But how do you account for the long-term changes in the CO2 factors?
It's a really good question. So one of the challenges of taking a net zero carbon approach is that you start to get very engaged about grid factors changing. I think one of the graphs we showed was the percentage of coal as part of the electricity mix for a number of countries and regions, and it has dropped dramatically. We've seen in the UK go from around 80% of our electricity generation from coal to just 20%, and it being planned to be phased out, I think by 2023, the last coal plant is due to go. So you do see these huge shifts, and the debate, we've been heavily engaged in the debate around what does that mean for system selection. And the conclusion tends to be that as the electricity grid gets cleaner and cleaner, it gets to the point where it makes no sense from a purely carbon perspective to be using any form of combustion, whether that's by natural gas or from other methods, particularly if you're getting efficiencies from heat pumps and so on. What you do find though is if you set the target of 0, it all cancels out to 0. So you end up, even though carbon is your framework, because we're concerned about the conversation being around climate change, if your target is 0, all things cancel out. And so the conversation around carbon factors ceases to be the thing that drives it, because you know you've got to cancel out your energy consumption with the energy generation to meet those needs.
Okay, regarding the Packard Foundation building, so looking a bit more at some of the detail here, did that graph include unregulated loads as well as regulated loads?
Yes, short answer. Let me just go back to the slide. So this involved a lot of work with the client and the end user to actually identify exactly what technologies were going to go into their building, and then what efficiencies those could, there we go, what efficiencies they could have from that plug load reduction. So that was looking at photocopiers, looking at computers, looking at monitors, looking at more energy intensive equipment, and just really seeing how much we can reduce the overall demand that we start with, which obviously then impacts on, you know, a capital cost investment of reducing the number of PVs, for example, that you would need to balance out. And it's also quite interesting to note, not on this particular project, but on another project that we've worked on, where we worked with a client in a very similar way, and this was actually, I think it was a lab or a medical building, and we identified that in the technology that they needed to do their high performance work from the lab equipment, that wasn't actually available at the time, and so we worked with them to develop a strategy. So looking at day 2, day 3 of the lifetime of this building, to make sure that when the technology that they need for this equipment comes online, it can be seamlessly integrated into the building. So we're not just looking at it always at day 1. I mean, that's our ideal, that's our target, but we also recognize that it's not always possible in all buildings, and we just need to facilitate a way that, you know, the end user or the developer or the client can achieve their aspirations over the lifetime of the building.
Just on the regulated versus unregulated, I think that it's become a particular issue with the European approach that we've had to energy labelling, because the demand has always been to compare apples with apples. So if you take the occupant behaviour out of it, or you standardise the profiles, we can compare one building to another and be confident that we're comparing the same thing. But the reality is buildings are occupied very, very differently by different users doing different things in what could be the very same building. And so this process that we've talked about really digging deep into when people will use the building and what their plug loads will be, is really important, because that net zero carbon definition or net zero energy definition is everything. It's the fuel bill at the end of the year, it's the carbon footprint at the end of the year that has to be cancelled out. And so that changes the mindset of us as designers, and it also means that we need to get much earlier insight into how the buildings will be used. And that can be a real challenge, particularly if you're doing speculative development. You know, how do you, what benchmarks should you use? What kind of error ranges should you be allowing for? And how do you deal with those error ranges? So what happens if an occupant comes into a building at double the density than might have been expected, or for that matter, half the density? And how do you share the responsibility for hitting a net zero energy target? And that's where this interface between the developer and the occupant is an interesting one, because it can then become part of your lease terms, that you're given a carbon budget as a tenant or an energy budget as a tenant, and if you go over those limits, you would be expected to invest in offsets to manage your excess consumption within that building.
Okay, yeah, well, that I think that pretty picks up on a comment from Herschel, who was asking whether you include regulated and unregulated loads. You include them all,
yeah, everyone.
Okay, great. Well, that's clear. Okay, so I had a question here about the tools that you use, and I've had a few actually which asked about some of the tools that you use. So this one was, I think, from Carl, and he was asking, what concept stage analysis tools do you use?
So what we tend to do is use the same tool set by and large throughout the design process, and what changes is the level of geometric complexity or space allocation. So a lot of the work that we do at concept stages will be using either IES or Energy Plus, using the HVAC simulation rather than any wizard. So it's not templated, it's actually real systems in a building rather than placeholders, as is the habit in the UK. And at the early stages, you're just modeling a box. You can learn an enormous amount about the ability of a building to hit a net zero target by modeling a very simple version of it, a shoebox, at the early stage, and throwing lots of different options at it. So this question about which lever do I pull and how hard do I need to pull it to make a change can be tested with those simple models, and then you only really need to get into the real detail and complexity later on. Now, from a UK perspective, that's not how we've been encouraged to work through the planning process and through the Part L process. We're modelling very, very complex geometries very early on often for questionable levels of improvement of accuracy, a lot of extra effort, and we're not actually then having the time to help the design team make decisions about what should work when. So in parallel with those energy simulations, we do a lot of quick modeling where we're producing vast sets of data, and we have a tool called Integral Drive, which we've developed out of our Vancouver office, which will run many thousands and millions of simulations of simple box models and use past models from old projects and chuck data at them. We'll create an enormous data set that we can then sit with an architect and play with slider bars and interrogate that big data set in real time, rather than going through the sometimes torturous process of saying, here's a design, go and model it, get the results. 2 weeks later, we haven't moved the design forward. So we're trying to find new ways of working that give that quick feedback.
And just to follow up on that, we spend a lot of time, making sure that we learn from previous projects as well. So although we use as simpler models as possible, obviously we take the lessons learned from other projects and apply them to those projects, which, especially when we look at the UK context, makes the well-known performance gap potentially between operation and the general modeling that you would do as part L, not so much on the performance engineering side. Whereas as a practice, we try and minimize that performance gap as much as we possibly can, using those lessons learned, working with clients, and making sure that we can take the data that we get from the developments that we've worked on, that we've modeled, that we can then go in and do a post-occupancy survey and gather all of that, and then use those lessons learned. So that's quite one of the key issues and one of the key drivers that we're trying to really work with particularly with the GLA in London at the moment, to make sure that that's kind of like embedded within a lot of all the major projects that are going on in London at the moment.
Okay, I think probably you've already answered this question in a way. So would you say that net zero should be divorced really from the whole EPC and DEC type activity? For those people, that's energy performance certificates and display energy certificates, which are used as part of the legislative framework in the UK.
So I think they end up being two things that happen in parallel. One of them, as designers, we need to focus on performance engineering, not compliance engineering. So asset ratings and certificates are there really as a safety net against really bad design decisions, whereas performance-based modeling, simulation design is about achieving excellence. And so you need both, because certainly within the regulatory environment we have here, that labeling scheme is important, and we have seen with property investors that the prices of properties where the EPC ratings are low, they get chipped, because the people acquiring them see them as risks in their portfolio, because they're looking themselves to decarbonize their portfolio, and they don't want to take on buildings that have poor energy performance ratings. But from our point of view, we need to be doing both in parallel. But we start with the performance engineering approach, and if you do that, you end up with a great EPC rating. You'll get the label that you want, but don't start with the label. Start the other way around.
A good point, I think. Now I've got a question here. This is from Dave Green. This is a chair of the CIBSE ASHRAE Group. He's listening from Canada, and Dave just asks, do you use, building on that last response really, do you use building analytics and automated fault detection routines to continually improve performance over time?
So we have a performance engineering team that work, a lot of them are based out of a Toronto office, but they're spread throughout the group, and they do a lot of work often on other people's projects. So that being the case, you don't want to be your own policeman. You're going in to understand how buildings are performing and getting the data from them. We are seeing a lot of opportunities now with lower cost sensors to kit out buildings with the kind of equipment that Dave's talking about, so we can get that real-time feedback. It's not the norm. It's quite hard to get that put into projects, and certainly within the UK context, it's a really early days for that kind of awareness amongst our clients. But we are actually seeing, in the last few months, we've had quite a lot of requests from property fund managers and so on to say, well, can you kit out our buildings? Can you put those sensors in so that we can see what's going on in real time and use that data to fine-tune performance?
Okay, thank you. I've got a question, or a few questions actually, from Aziz, and he's asking about the climate zones. He says, well, we've got 7 or whatever, we break it into climate zones in the globe, around the globe. How can you apply these principles to all climate zones? Are they applicable?
Yeah, so Nathan, maybe if we flip to the pathway that we showed at the beginning, the process of discovery, of finding out what works for you in your context, that step 4, understand the context, is incredibly important. And that includes the environment, includes the climate. Decisions that we'd make for a building in Beirut are going to be vastly different to decisions for a building in northern Canada. What they will share is a design process that is around discovery, simulation, testing, and also thinking about those unintended consequences. So we've been doing work recently looking at the overall whole life cycle carbon impact of buildings, and you can find that in certain circumstances, if you choose the wrong facade, it can be better to have a highly glazed facade in what we would consider a real cooling dominated environment, such as the Middle East. It may be better in terms of overall life cycle carbon to have more glass than less. And these are really counterintuitive data that we're having to grapple with, and then posing questions back to facade designers about, well, surely you can reduce the embodied impact of the facade so that we can get that back into balance. So for every climate is different. There are solutions that work for all. So what works in the cold climate, where we have insulation playing a huge part, air tightness playing a huge part, but much less resource in terms of, say, solar energy, is then offset in those other climates where we've got far higher renewable energy resource. So it's a balancing act. And as we said, that we're not dogmatic about producing net zero energy buildings just on site. If we set that as a target, we get as far as we can, and then the conversation has to be about where can we generate any excess that we can't accommodate on site.
Okay, I'm going to try and mop up a number of these questions in one. You've spoken about the energy consequences of a building, but Carl asks about the embodied, not only the embodied carbon of PVs, but the chemicals in there. And Salam makes a comment: is how can you actually think of the outdoor air being fresh? But I've got someone who actually says, how do you actually incorporate the indoor air quality and thermal comfort in the net zero energy context?
Okay, so I took 2 questions out of that, one on embodied carbon and then one on indoor environmental quality. I'll do the embodied. I'll touch upon the embodied first. I mean, and this comes back to, so for example, in the UK, the decarbonisation of the grid. So if we say that, you know, our operational energy is going to be met by an ever cleaner grid and a grid ever growing in the amount of renewables that is going to go in there, it means that the equipment that we're actually going to be using becomes more important. So for example, if we look at air source heat pumps, for example, the embodied carbon that makes up that equipment is going to be key, such as the potential refrigerants that are going to go in there, the global warming potential of those those refrigerants. Now, also for the embodied carbon of PV, you know, it's a similar conversation to be had, and it's changing the narrative. It's making us look to other issues, other items that we need to consider.
I think one of the queries was the unexpected consequences. So perhaps Carl mentioned the chemicals that may be difficult at the end of lifetime to actually deal with. Is that something that comes into the overall assessment?
That's not something that I've looked at in any great detail, so I don't think I'll be the best person to answer that question, unfortunately.
Okay, I think it's a challenging one to address in actual fact. So that's fine. The other query you were just gonna look at, I think there was the IAQ and
yeah. So I mean, these are some of the supplementary consequences, if you will, that we have through passive design, good design, whereby we can rely on, you know, exposed thermal mass using radiant surfaces. These direct outside air plant. These are all systems and design responses that generally create more comfort for an occupant. We're not relying, and as a consequence, we're not relying so much on more energy intensive cooling and heating requirements. So they, it comes almost hand in hand, if you will, as a direct consequence of, targeting the net zero. So, for example, as the example of the hospital in Beirut, the ultimate target that we sat down and said, can we make it a net zero building? Unfortunately, in this particular case, we couldn't, but we had all of these knock-on consequences that improved into indoor environmental quality.
I think just quickly to add to that, the challenge of outdoor air, and it's an interesting point about whether it's fresh air or not. In the UK, we'd say fresh air rate. Our American colleagues would always remind us to say outdoor air rate because you can't legally guarantee that it's fresh, and they're probably right. And it's true in the case of Beirut. If you look at the air quality in Beirut, it's absolutely terrible, and it's partly terrible because people are using diesel generators to bridge the gap between a grid that's not reliable when it's on, when it's off. They're using the generators. So sometimes you have to take tough choices around, would you rather a building, if it was without power for a month because, say, the electricity grid's been taken out by an act of war, which is the reality, would you rather that building and the occupants be exposed to air that's not of optimal quality, but that building to keep surviving, keep functioning, keep providing an essential service to the people? But in a more general sense, we find tough environments. So the case study, we looked at the cost benefits of environmental performance on employee costs. That actual project is next to a cement batching plant and adjacent to a very busy road and a railway. So you've got brake dust, you've got emissions from concrete batching, you've got all that other stuff in play. And so you say, well, actually, if I can get the cooling loads down, if I can meet those cooling loads by primarily by hydronic systems rather than using all air systems with lots of fan power, I can then actually absorb the extra energy penalty of high levels of filtration on my incoming outdoor air so that it can be delivered in a state which would lead to good air quality. And then how it's delivered into the space, thinking about the distribution of that air becomes the next question. So whether it's mixing, whether it's supplied near the occupant, and that's where they're kind of those quick tools about CFD. Can we just chuck it in, find out where it works? Is the air actually going to hit the occupant at the right temperature? Is it going to cause discomfort? Are we going to hit those thermal comfort criteria? So we're being asked more and more, particularly by tech clients who've got very aggressive expectations on air quality and comfort, to produce answers to those questions very quickly and many times in the life of a project. So it's been a big focus for our analysis team over the last 3 or 4 years, has been to develop the tools that allow us to do that.
Thank you both for your time and your insight and sharing your knowledge today. Thank you for joining us, and we look forward to joining with you again in the near future for another CIBSE ASHRAE Group event. Thanks very much and goodbye.